Section 9.4, simplifying radical expressions using properties of radicals. So we start with what's called the product property of radicals, which if you have matching indices in a multiplication of two radicals, then you can combine and multiply together what's underneath those radicals. So square root of 7 and square root of 2 are both square roots, so I can just combine the 7, 2 and make 14, and then always double check that you can't simplify any further, which you can't, so that's our answer. Cube root of 3, cube root of 11 is going to be cube root of 33. Again, nothing simplifies further there. Square root of n plus 4 times the square root of n minus 4. We're going to have some foiling going on there. So we get n squared minus 4n plus 4n minus 16, which is the square root of n squared minus 16, and that's the end of it. Even though n squared and 16 are both perfect squares, because they're connected with a subtraction, you cannot break up the square root. So this does not equal n minus 4, as maybe one would want to do. And then part D, the fifth root, 7 times 3 is 21, 8 to the third and 8 to the first is 8 to the fourth. Now what we're going to do is you're going to use the product property to simplify radicals. And how this is going to work, we're going to first break up the given problem into the product of two radicals, one of which is a perfect radical. We're going to solve the one that's perfect and leave the other as a radical expression. For variables, a perfect root is one whose exponent can be divided by the index. And you'll see in the directions the statement, assume all variables can be any real number. This adds an extra step that we're going to have to incorporate to ensure that we're never trying to mix even roots with negative numbers, because that's not a good plan, right? Square roots of negatives or fourth roots of negatives don't exist. So the extra step is that if there is a variable under the even root and the result is an odd exponent, that variable must be placed in absolute value. So we have these three conditions. We have an even root, an odd exponent, then we make absolute values on our answer. So example 2, simplifying the radical. So I have the square root of 24, so I don't know what the square root of 24 is, it's some random decimal value. But if I think about numbers that go into 24, one of them is a perfect square, and that would be 4. So 24 could be rewritten as the square root of 4 times the square root of 6. And then I solve the square root of 4 equal to 2. The square root of 6, we don't know the answer, so that's what we have. For 128, I'm looking now at perfect cubes, and this is where a calculator could be useful. Hopefully you have the first few perfect cubes memorized, and so we would check 128, so it does divide by 8. 8 is a perfect cube. However, we want to make sure we find the biggest perfect cube that goes into it. So 8's kind of on the small side when we're comparing with 128. So I'm going to try a couple larger values. If I take 128 divided by 27, which is the next perfect cube, we get a decimal. If I take 128 divided by 64, it equals 2. So that's what I'm going to use. I'm just going to carry down that 2 in front, and I'm going to break up 128 into 64 times 2. It's really important to keep your notation. Make sure you keep the cube root in the index. So then we can solve the cube root of 64 is 4. And I don't know the cube root of 2, so that one just stays in radical. And then I can multiply the 2 and the 4 to get 8 cube root of 2 as my final answer. Letter C is the square root of 75z squared. So I'm looking at 75. Perfect square going into 75 is 25 times 3. And then for the exponent on the variable, it does divide by the index because the index is also 2. Right, that was one of the statements up here. A perfect root is one whose exponent can be divided by the index. And so what I'm going to do to solve this problem for the square root of z squared is I'm going to go ahead and take the exponent and divide it by the index. So I'm going to get z to the first power. So I have 5z square root of 3. But when I'm working with variables, I have this extra step I have to watch out for. Since the directions say variables can be any real number, what I need to make sure of is that I'm playing nicely with square roots and negatives. And so since I have an even index, being a square root, and an odd exponent on my answer, being a 1, my z must be put into absolute values. And that's just to make sure that it's a positive number so that the square root thing actually works. Right, 32, y to the 8th. So think about what goes into 32 that I know the square root of, making sure I get the biggest perfect square is going to be 16 times 2. My exponent of 8 will divide by my index of 2, so no need to do anything further there. So I have 4. 8 divided by 2 is 4, square root of 2. And now I stop to think, do I need absolute value? And the answer is no, because I had an even index, but I also have an even exponent. All right, even exponents make your answer positive. So that's why we don't need absolute value to make the answer positive. All right, part E, here we're going to see, let's see, 48 is 16 times 3, but this time my exponent does not divide evenly by my index. So what I need to do is I need to take these 3 x's and I need to break it up into one group where the exponent will divide by the index. So let's say 2, since 2 divides by 2. And then the other group is how many I have left, which is just 1, because together they would make x to the 3rd. So I can solve out 16. The square root of x squared is the absolute value of x. And then I'm just going to rearrange the problem. So all of my non-square roots are together, and my square roots I combine underneath a single radical. So let's do another one where the exponent will not divide evenly by the index. So letter F, we have the cube root of 8, which is perfect. All right, 5 does not divide by 3, so we need to split up these a's. Working my way down from 5, the first number that divides by 3 is 3 itself, which means there are 2 more a's to put over here. So together they make a to the 5th. But what I have is one group that will divide evenly with its exponent and index, and the other group that won't. And then 12 does divide evenly by 3, so I don't have to do anything with the b's. So now I have 2a, no absolute value needed because it's an odd index. And then I have b to the 4th cube root of a squared. And we do have a few more problems to work out, but we'll do that in the next video.